Have you ever felt like you're just drowning in data, but you're absolutely starving for real answers? Well, today, we're going to put on our detective hats. We're about to crack a real-world business mystery, not with a magnifying glass, but with the raw power of data, using the Six Sigma Analyze phase as our official detective kit.
So, here's our case file. A shoe company is on the edge of a huge decision. They've got two different sole materials. Material A, kind of the old reliable, and Material B, this promising new contender. They have to know which one lasts longer before they sink millions of dollars into production. But here's the catch. Their only clues come from a tiny little set of test data. So how in the world do they make the right call without just flipping a coin?
And let's be clear, this is not just about picking the better material. A single wrong move here could completely destroy years of customer trust. I mean, you're talking about complaints and returns going straight through the roof. This decision has to be built on a foundation of solid, statistical evidence. Guesswork? Not an option.
Okay, so every great investigation starts with gathering clues. But right away, we face a massive challenge. We can't possibly test every single shoe the company could ever produce. I mean, that would be a logistical nightmare. So we've got to be incredibly smart about how we collect our evidence. First, let's just map out the entire crime scene. In statistics, we call this the population, and you have to understand this is a truly huge concept. It's not just some of the data, it's every single data point that has ever existed or ever will exist for these materials. Seriously, think about that. The durability of every shoe sole ever made and every single one that could be made in the future, it's the whole universe of possibilities we're trying to get our heads around.
Now, since we can't test an entire universe, we collect a sample. These are our fingerprints, our DNA evidence, our key clues. It's a small, manageable little piece of that population that we can actually get our hands on and analyze. For our shoe company, it's that limited number of soles they actually put through the ringer in those durability tests.
And this, right here, this is the whole magic trick of what we call inferential statistics. We take the specific clues we find in our small sample and we use them to draw these powerful conclusions, or inferences, about the entire population. We're using the evidence we can see to understand a much bigger truth that we can't.
Okay, I know what you might be thinking. Hold on a second. How can we really trust a handful of clues to tell us the truth about millions of shoes? It feels like a huge leap of faith, right? But it's not. It's because of this fundamental, almost magical rule in statistics that makes this whole detective thing possible. It's called the Central Limit Theorem.
Just picture this. We take a small sample, say 5 shoes, and we calculate their average durability. Easy enough. Now we do it again with 5 different shoes, and we do it again, and again, maybe thousands of times over. Then we take all of those individual averages and we plot them on a chart. What you see next? Well, it's pure statistical magic. Even if the durability numbers for individual shoes are all over the place, just completely random and chaotic, the distribution of their averages will always form a perfect, predictable, normal bell curve. This isn't just a coincidence, it's a mathematical certainty. And this theorem is the bedrock of our detective work. It gives us a predictable pattern we can actually trust and measure against.
All right, we've gathered our clues. We now know they behave in a trustworthy way. So now it's time to take our case to the courtroom. We need to form a really clear theory about our main suspect, Material B, and we're going to put it on trial, using our data as the star witness. And this whole formal process is called hypothesis testing.
So in our statistical courtroom, there are always 2 opposing arguments on the table. First up, you've got the null hypothesis. You can think of this as the legal equivalent of innocent until proven guilty. It's the default assumption that, there's no real difference between the materials. Then you have the alternative hypothesis. That's our prosecution's big argument, which boldly claims that yes, there is a significant difference to be found here.
You know, this quote just makes the whole concept crystal clear. The null hypothesis, or H0, represents the boring old status quo. The sky is not falling. Nothing to see here. The alternative hypothesis, or HA, is the exciting, disruptive claim we're actually trying to prove. The sky is falling, or, for our case, Material B really is better.
But you know, just like any trial, there's always a risk of a miscarriage of justice. Our statistical jury can make one of 2 big mistakes. A type 1 error is a false alarm. We convict an innocent party. We conclude there's a difference when there really isn't one. Then there's a type 2 error, and that's when we miss it. We let a guilty party walk free, failing to detect a difference that truly exists. A good data detective's job is to carefully manage the risk of making either of these errors.
So how does our jury finally reach its verdict? Well, it needs a single objective measure of how strong the evidence is. Is it compelling enough to reject that innocent theory and declare there's a difference? This brings us to the dramatic climax of our entire case, the p-value. After all the tests, all the analysis, our statistical jury comes back with a single, powerful number. A number that holds the key to this whole mystery, and that number is 0.034. This is our smoking gun. But what on earth does it actually mean?
The p-value tells us the exact probability that we would see a difference this big in our sample just by pure random chance. In our case, there's only a 3.4% probability that our results are a complete fluke. And since that chance is so low, well below the standard 5% threshold we use for reasonable doubt, we can confidently reject the null hypothesis. The verdict is in. The difference we saw is real.
But hang on, a guilty verdict isn't the end of the story. Any good detective knows that a statistical finding is pretty much worthless until it's translated into a smart, real-world action. So the final and most crucial step is figuring out what this verdict actually means for the business.
And this is where we hit a really critical distinction. Statistical significance just asks, is this difference real? Our p-value already answered that with a big yes. But practical significance asks a much tougher business question. Is this difference big enough to actually matter? Sure, material B lasts longer, but if it only lasts, say, 5 minutes longer and costs twice as much, is it practically worth it? That's the final judgment call. By weaving together that statistical proof with practical wisdom, our shoe company can now make a confident, data-driven decision. But look, this data detective kit isn't just for shoes. It can crack cases in marketing, finance, operations, anywhere you have a burning question. So the real question isn't just what mysteries are out there waiting for you to solve, it's what are you going to do with the answers you find?